Welcome everyone. This is TCS seminar at Jagiellonian University. Last talk in the semester. Marek Skrzypczyk, student, supervised by Andrzej Grzesik, co-supervised, yes, by Andrzej and by Michał Wojtylak. So the talk will be about oriented graphs and antidirected paths in oriented graphs. The floor is yours.
Thank you very much. An oriented graph is a graph with an orientation on every edge. Yes, and we have a graph. We give an direction, exactly one direction on every edge, for instance. Okay, and if we have an edge U, V, then we say that U is an in neighbor of V, and V is an out neighbor of U. Okay, and the integree of U denoted by D minus U is a number of in neighbors of U. And similar, the out degree denoted by D plus U is a number of out neighbors of U. Okay, and the minimum semidegree of graph G denoted by delta plus minus G is a minimum among all out degrees and in degrees in our graph. Okay. And the new definition is the minimum pseudo semidegree. Okay, and the minimum pseudo semidegree is denoted by bar delta plus minus G, and the minimum pseudo semidegree is 0. If G has no edges, yes? And otherwise, the minimum semidegree, pseudo semidegree, is the largest integer D, such that every vertex has out degree either 0 or at least D. And the same for in degree. And in degree either 0 or at least. So we allow that vertex have no out neighbors or in neighbors, yes? And clearly the pseudo semi-degree is more than or equal minimum semi-degree. Okay.
Now that you've written it out, could you perhaps repeat that?
The definition, yes?
Yeah.
Okay, the minimum pseudo semi-degree is 0 if G has no edges, and otherwise minimum pseudo semi-degree is the largest integer D, such that every vertex has out degree either 0 or at least or D, and in degree either 0 or at least D.
So if there is a vertex of out degree 1, then this pseudo semi-degree minimum is 1, then, yes? Or?
Yes.
Okay. So you kind of, in this definition, you take a minimum, but you kind of ignore 0.
Yes.
This is saying,
Yes.
Okay, I got it.
Is there some explanation for why we ignore zeros? Do they always happen?
I guess there will be statements in the moment, yeah. But it's not default, at least. I didn't see it before. I didn't see it before, so it's most interesting.
Okay, and then anti-directed path, shortly anti-path, is an oriented path such that each vertex has either 0 out degree or 0 in degree. Yes, for example. Yes, each vertex, one vertex has in degree, out degree 1, yes, and in degree 0. This vertex has in degree 1, out degree 0, and other vertices has either out degree 2 and in degree 0, or in degree 2 and out degree 0, yes? And if the number of edges is odd, then we have one type of antipath. And if the number of edges is even, then we have two types. Yes, number of edges is even. with two types of antigraphs. Yes, here we have antipath with first and last vertices with out degree 1, and this antipath has first and last vertices with in degree 1. Yes, so for even length we have two types of antipaths. Okay, and similar we define antidirected cycles and shortly anticycles. But for anticycles, the number of edges must be even, yes? Number of edges must be even because otherwise we cannot obtain an anticycle. Okay, and the length of antipath of anticycle is the number of edges, yes? Okay, and in the first theorem in 1981, Jackson proved that every oriented graph with minimum semi-degree more than or equal k contains a directed path of length 2k. And this is a directed path. And natural problem is to find bounds for other orientations, yes? And Stein conjectured in 2020 that every oriented graph with minimum pseudo-semi-degree more than k over 2 contains each oriented path of length k. And Stein, together with Klimoshowa, considered the conjecture for antipaths and with minimum pseudo-semi-degree. And they conjectured.
Can you hear me? What do you mean that it contains each connected path?
Each oriented path.
Each oriented path.
Because
of each length? You mean of each length, or?
No, because we have a few possibilities of orientation. Yes.
Of you mean antipath, not path. You mean it contains each connected antipath. Each or
oriented, not oriented path, not antipath.
okay.
Okay, and conjecture 3.
You are missing the length of the path.
Of length k, yes. K. thank you. Okay, and Klimoszowa and Stein in 2023 conjectured that every oriented graph with minimum pseudo semi-degree greater than k over 2 contains each antipath of length k. Each antipath, because for even number of edges we have two types of antipaths, yes? Okay, and in the same paper they proved the conjecture for 3k minus 3 over 4. Yes, the minimum pseudo semi-degree is greater than 3k minus 3 over 4. Then G contains each antipath of length k. Okay, and to prove this theorem, we need three auxiliary lemmas. First lemma. If the minimum pseudo semi-degree is more than or equal k over 2, m is the length is the number of edges, m is the length of the longest antipath, and if m is smaller than k, then m is odd. This is first auxiliary lemma. And second, if the minimum pseudo semi-degree is greater than k over 2, G contains an anti-cycle of length m plus 1, and m is smaller than k, then G contains an antipath of length m plus 1. And the last auxiliary lemma if the minimum pseudo semi-degree is more than 3k minus 3 over 4, m is the length of the longest antipath, and m is smaller than k, then G contains an anticycle of length m plus 1. So the last lemma implies our bound in theorem 4, yes? Because if you have a anticycle of length m plus 1, then by lemma 6 we contain an antipath of length m plus 1, so this contradicts with our assumption with about the length of our antipath. Okay. Okay, and Chen, Hu, and Zhou improved this bound. They showed that every oriented graph with minimum pseudo semi-degree more than 2k over 3, then G contains either an antipath of length k plus 1, so longer antipath, yes, or anti-cycle of length k plus 1, so this theorem is slightly different. Okay, and the next result is Kokan and Tiomkin. Kokan and Tiomkin showed about 5k over 8. Yes, and G contains each antipath of length k. And together with my supervisor Andrzej Grzesik, we proved the bound for k plus square root of k over 2.
You're missing the line.
Thank you. Our paper is not published yet. Okay, and our bound is k plus square root of k over 2. Okay. Okay, so now I will show some definitions, assumptions, and claims that we need to prove our theorem. So, let A be the longest antipath in our graph. Okay, and by the lemma 5, yes, we may assume that M is odd. Okay, and if we find an anticycle of length n+1, then by lemma 6, there exists an antipath of length n+1. So we may assume that G doesn't contain an anticycle of length n+1.
M could be even, and then this is trivial, right? M could be even.
Yes.
And then this is trivial. Yes. Oh, M is not trivial. Sorry.
M is odd. If M is even, then we create
because
the
lemma
longer.
5 says that M is okay, sorry. Yeah.
We assume that G doesn't contain an anticycle of length n+1.
Is this may assume or no?
We may assume this because otherwise, if we find the anticycle, then we find the longer antipath, yes, by lemma 6.
So we know.
Okay. Okay, and this is our antipath. V0, V1, V2, and so on, Vm. Okay. And if we have an edge V0, V2i plus 1, yes, V2i plus 1, V2i, then we obtain a new antipath, yes, because we start in V2i, yes, we go to V2i minus 1 and so on to V0, V2i plus 1, V2i plus 2, and so on to Vm. Yes, so we obtain the new antipath of the same length. Okay, and let E be the set of vertices with even index on A. And respectively O be the set of vertices with odd index in antipath. Yes, and we may assume that each edge in antipath is directed from E to O. We may assume that each edge on A is directed from even to O, that's from E to O. Okay. Okay, and if you have the edge V0, V2i plus 1, yes, then we obtain a new antipath of the same length. And we define the set S. Let S be a subset of O, be the set of second vertices. Second vertices in some antipath on the vertices on the all vertices in VI that can be obtained by the above operation. That's the second set of second vertices. Yes, for instance, V1 is second. Yes, because performed as a second vertex in this antipath. Yes, and similarly, if you have the edge V0, V2i plus 1, then V2i is first vertices on this antipath, and then V2i minus 1 is second. Yes. So V1 and V2i minus 1 is second. Okay. And how large is the set S? Okay, and each edge from V0 to set of vertices with of the index to the set O creates a new second vertex. Yes. Yes, if you have V0, V2i plus 1 is an edge, then V2i minus 1 is second. Yes. So the size of S is more than or equal the number of out neighbors from V0 to O. That's the number, the edges to the set of vertices with odd index, minus 1. Why minus 1? Because the edge V0, V1 and V0, V3 creates the same second vertex V1. Yes, so we must subtract the one. Okay. And similarly, we can create the penultimate vertices. And by symmetry, V0, Vm, and by symmetry, we may have an edge V2i Vm, and then we obtain an antipath V0, V1, and so on, V2i, Vm, Vm minus 1, and so on, and V2i plus 1. Yes, so V2i plus 1 is a new last vertex. So then the vertex V2i plus 2 is a penultimate. Yes, przedostatni. Yes? So P is a subset of vertices with even index. B the set of penultimate vertices. Yes, so Vm minus 1 is penultimate, yes, and V2I plus 2 is penultimate. Okay. And in similar manner, we can show that the size of of P is more than or equal the number of neighbors of Vm in E. Yes. Okay. Okay. And our first claim, 11. There is an edge from V0 to P or from S to Vn. Okay. So assume that there is no such edges, yes? Then the number of edges from V0 to E is less than or equal m minus 1 over 2, so the number of all vertices except from 0 in E, minus, we have now edge to P, minus P. Yes, so we don't have the edges to P. So the number of edges from V0 to out vertices is more than or equal minimum pseudo semi-degree and minus this, yes, minus m minus 1 plus P. So, and applying our bound for set of S, we obtain that S is greater than or equal this minus 1, yes? So, minimum pseudo semi-degree minus m minus 1 over 2 plus P minus 1, yes? And this is greater than P. Yes? And using the similar formula for S and Vm, we obtain that P is greater than S. Vm and S, we obtain that P is greater than S. S, so which gives a contradiction. Okay. Okay, so by this claim 11, we may assume that there is an edge V1, Vm. Yes, there is an edge from S to Vm, in particular V1, Vm. If not, we can relabel the vertices to obtain V1, Vm.
V1 or V0?
V1, because V1 is second.
Oh, V1 is second.
If you have V0, Vm, then we have anti-second.
Yes, yes, yes.
Okay, so if you have this edge, this implies that V1 has positive out degree and in degree. So all the neighbors cannot belong in the antipath. Some neighbors must be outside. So let F be the set of in neighbors and L be the set of out neighbors. Okay. And together the number of vertices in F and L is greater than or equal to minimum pseudo semi-degree. That's because V1 has positive out and in degree. Minus number of these vertices. We assume that V0 is in F, yes? So the number of these vertices is m minus 1, so minus m plus 1. So m is smaller than k, so this is greater than or equal to times minimum pseudo semi-degree minus k plus 2.
Could you explain again the first inequality? I didn't get it.
Yes? Inequality?
Yeah.
Okay. This subpath, yes, has m minus 1 vertices.
Mm-hmm.
Yes, because we don't count the V0 and V1. So V1 has a positive number of out degree and in degree.
Yes.
So the number of all neighbors is at least 2 minimum pseudo semi-degree.
Yes.
And minus number of these vertices, as this is our bound for F.
No, because you. Okay, so you don't count the neighbors that are already in the path, that's what you say? Or there are no neighbors in the path? By definition, these are neighbors that are outside.
Mm-hmm. Yes.
Because there may be some neighbors inside, but you don't count them.
Mm-hmm. Yes.
Okay, I understand.
Okay. And we may assume that F, by symmetry, we may assume that F is greater than or equal half of them. So pseudo semi-degree minus a over 2 plus 1, and this is greater than or equal 1, greater than or equal 2. Why? Because the vertices in L also creates an antipath of length m, because we start in V2, V3, and so on to Vm, V1, and we finish in the vertex in L. Yes. So in these types of antipaths, V1 is penultimate. Yes, so by symmetry, we may assume that F is larger than or equal L. Okay. And the next claim. Okay, if V and W belong to F, v2I is an edge, W v2I plus 1 is an edge, then W v2I minus 1 is forbidden, and W v2I is forbidden. And the proof. Okay, this to A to A plus 1 to A minus 1. So V and W. Okay, we have an edge V to I. We have edge W V to I plus 1. Okay, and if we have the edge W V to I minus 1, then we obtain the longer antipath, yes, because we start in V to I, V, V1, and so on to V to I minus 1, W, V to I plus 1, V to I plus 2, and so on to Vm. Yes, so the length is m plus 1. And if you have the edge W, V to I, similar, we have the longer antipath V to I minus 1, V to I minus 2, and so on, V1, V, V to I, W, V to I plus 1, and so on, Vm. Yes? Okay. Okay. Okay, and the last claim, yes, the last claim. Okay. Let I be the integer. Let I be integer is less than or equal m minus 3 over 4. Then there exists at most 2f plus 1 edges from f to the quadruple v for I, v for I plus 1, v for I plus 2, v for I plus 3. Okay. So assume that there exists a vertex there exists a vertex in F with 4 out neighbors in Q equals V for I plus 1, for I plus 2, for I plus 3. Okay, so assume that there is such vertex. So for I plus 1, for I plus 2, for I plus 3.
So I don't understand how does the statement of the claim relate to that. So in the claim you have that there are at most 2 F edges plus 1.
Yes.
Here you
from
there is a vertex which sends 4 edges to consecutive vertices on
yes.
A.
We first assume that there is a vertex in F with 4 out neighbors. Yes.
It's just the case. Yeah?
Yes.
Yes.
Okay. So, yes. Okay. So.
And these edges are directed towards the.
Yes. From F to Q. Okay. So if you have such a vertex, then if you have other vertex in F, then by this claim 12, this edge is forbidden. For I plus 2 is forbidden.
So that is another vertex in F, yes?
Yes.
Okay.
And simultaneously, these 2 edges are forbidden. You may have only at most one of them. So together, we have 4 vertices and other f minus 1, 4 edges and other f minus 1 vertices. Each has at most 1 edge. So together, we have f plus 3 edges from F to Q, and this is smaller than or equal to F plus 1, yes, because F is at least 2. And case second, there are 2 vertices in F with 3 out neighbors in Q. So if you have 2 vertices in F with 3 out neighbors, then we have a pair 2j plus 1 such that V has an edge to 2j and 2j plus 1, and V has an edge to 2j and 2j plus 1. And then we obtain the longer antipath by claim 12. So we may assume that only one vertex has at most 3 out neighbors in Q, and other vertices have at most 2 vertices in Q. Yes.
So you have so V and W are one of the two vertices of the assumption.
Yes.
And they have 3 out neighbors. So why do they share 2 consecutive neighbors? It must be the case.
Because we have 3 out neighbors in Q, so we have V for I is an edge and V for I plus 1 is an edge. And V for I plus 2 and V is an edge. And similar for W, yes? So there exists a common pair, yes?
But not consecutive, right? Must,
Ah.
Yeah.
Yes. So if you have this situation, then either V for I plus 2 is not an edge, or W for I plus 3 is not an edge. And similarly, either W V for I plus 2 is not an edge, or W V for I plus 3 is not an edge. So yes, this implies that W and V have edges to both for I and for I plus 1.
So let's read this together. So V and W are the 2 vertices in this description of the case, yes? And now either V for I plus 2 is not an edge, and this or W for
If you have both those edges, it's exactly the picture in claim 12, which is excluding 2 edges, so you cannot have 3 edges.
Okay, so this cannot happen. No, so one of this.
One of them is not an edge.
It's not an edge, okay.
Similarly, one of them is not an edge.
Okay.
But
And
it
this
has
is
2
W.
edges.
2 non-edges. Yes.
So both V and W are sending edges to V for I and V for I plus 1.
Okay. Yeah. So you can come back to your case now.
Okay, so we have one vertex with at most 3 out neighbors in Q, and other vertices have at most 2 out neighbors in Q. So together 2F plus 1. Okay, so the main theorem. Okay, So if the number of vertices in our antipath is divisible by 4, then we have m plus 1 over 4 quadruples, yes? So using the claim 13, we obtain that we have at most m claim 13, we have at most m plus 1 over 2 f plus m plus 1 over 4 edges from f to our antipath. This is the case with 4 is the number of vertices is divisible by 4. If not, then remains the pair Vm minus 1 and Vm. Yes? So, quadruples, yes, vertices. Yes, if the number.
This m plus 1 over 2 times f comes from m plus 1 over 4 times 2f, yes?
Yes.
That's okay.
Okay.
Plus
Yes, well, we have
one.
m plus 1 vertices.
M plus
yes?
1 is the last function. Okay.
Okay, so if the number of vertices is not divisible by 4, then remains a pair Vm minus 1 Vm. So, but we don't have the edges from f to Vm because we obtain an anticycle. So we have at most f edges from f to this pair. Yes, all edges goes to Vm minus 1. Yes, so together we have for this pair we have f edges. So f is smaller than half of them. So this bounds holds also for the case if the number of vertices is not divisible by 4. So by the other hand, each out neighbors of f belongs to our antipath because otherwise we obtain the longer antipath. Yes, so the number of edges from f to VA the number of edges from F to VI is at least mu to the same degree times F. Okay, so this bound m plus 1 over 2 times f plus m plus 1 over 4 is less than or equal k over 2 times f plus k over 4. Since the m is smaller than k, so combining these two bounds, we obtain that k over 4 is greater than or equal minimum pseudo semi-degree of g times minus k over 2 times f. Let's combine these two bounds. Okay, so f is greater than or equal pseudo semi-degree minus k over 2 plus 1. So we obtain okay, so applying our bound k plus square root of k over 2, we obtain that square root of k over 2 times square root of k plus 2 over 2, and this is greater than k over 4, which gives a contradiction. Okay, so this is a proof of the our theorem, and the last thing is okay, in conjecture 14. Okay, and Addario-Berry, Havet, Linhares Sales, read and Thomassé, 2013, conjecture that every oriented graph with more than k minus 1 n edges contains each anti-directed tree on k plus 1 vertices. Okay, and Klimosova and Stein showed that every oriented graph with more than cn edges contains an oriented graph with minimum pseudo semidegree more than c over 2.
This is a theorem or conjecture?
This is conjecture. This is not lemma.
So this is true.
Yes, this is true. And using this lemma, we obtain the corollary. That every oriented graph with more than k plus square root of k and edges contains each antipath of length. Okay. Thank you.
Thank you very much. Just stop the recording.